So far you've seen how we can use our trigonometry to find an unknown side in a right triangle. Well, now I'm going to show you how you can use our trigonometry to find an unknown angle in a right triangle. So recall that we can use a calculator to find a trig ratio from an angle. So we could, if we knew that we had a 35-degree angle in a triangle, we could type into our calculator sine of 35, and we'd be told a decimal number which represents the ratio of the opposite side to the hypotenuse side. Well, our calculator can also do the opposite. So for example, let's say we have an unknown angle x in our triangle, but we know the ratio of the adjacent and the hypotenuse. So we know cos x is equal to 1/2. Well, we can use our calculator to find the unknown angle x by using what's sometimes called the inverse cosine function. And what it does the opposite of cosine. So you type in cos to the -1 of 1/2, and that spits out the unknown angle. So your calculator is going to have a cosine to the -1 button that I want you to try to look for now. It's often above the cosine button, the regular cosine button, in yellow letters, which means you'll usually have to type in a second function and then press the cosine button to get cosine with a little -1. So I want you to try to do that right now and test to make sure that you get the right thing here. So go ahead and try to type in cos -1, or inverse cosine, of 1/2. And you should hopefully be able to get your calculator to spit out 60, or 60 degrees, for the unknown angle. If your calculator is giving you some other value, or you can't find that cosine to the -1 option, please contact your teacher and they'll be able to help you. Send a picture of your calculator to your teacher, and they should be able to help you say these are the steps you have to press to get that result. So now I'll show you how we can do this for a triangle. So we want to find angle theta, rounded to 1 decimal place. Well, here it is in the triangle, and it looks like we know the opposite side and the adjacent side. So for our 3 trig functions, tangent is the one with opposite and adjacent. So we could say that tan of angle theta is equal to opposite over adjacent, or tan theta is equal to 8 divided by 5. We're going to use our inverse tan function, which is that tan -1 of 8 over 5. Now you could either type that in as tan -1 of 8 over 5, or you could do 8 divided by 5 and get a decimal, and then type in tan -1 followed by that decimal value, whichever way you're most comfortable to do it. But either way, if we do that and we type that in, we should get that the unknown angle theta is equal to 57.995. So we're asked to round to 1 decimal place. So in order to round that to 1 decimal place, this 9 is going to make the other 9 round up. So angle theta is 58.0 degrees. When we used sine, cosine, and tan to calculate the unknown side lengths of triangles, we were able to use the diagram to figure out if our answers were reasonable, if those side lengths were reasonable answers for that triangle. We can do the same thing when we calculate angles. So as long as our diagram looks pretty good, and I'd say it does, the 8 centimeter side is a little bit longer than the 5 centimeter side, but it's not too much longer. So that means that the diagram should give us a reasonable estimate of how big the angle should be. So if I sketch what a 90-degree angle would look like, and then what a 45-degree angle would look like, we would probably expect angle theta to be a little bit bigger than 45 degrees. And sure enough, we got 58, which is a little bit bigger than 45 degrees. So yeah, I would say that the answer we got, theta equals 58 degrees, is a reasonable answer.